As a side note, it's important to understand how endianness affects the transaction hashing process. When transaction data is ordered and serialized into individual fields, you may notice that some fields don't match their original values. This occurs because endianness reverses the byte order of fields representing numeric values, while fields representing byte streams remain unmodified. Since byte ordering only applies to numeric values, fields containing just 2 hexadecimal digits, a single byte, will appear the same, as endianness only applies when it takes more than a single byte to represent a numeric value. Since hashes and scripts are byte streams, they have no inherent endianness. Although scripts can, and often do, contain numbers, these fields are treated as byte streams during transaction hashing and therefore remain unaffected by the endianness conversion. To understand why this happens, it helps to think in terms of decimal numbers rather than hexadecimal values. Consider the decimal number, 12,345. We naturally read this in big endian format because the most significant digit appears first, on the left. The number actually represents 10,000 plus 2,000 plus 300 plus 40 plus 5. In little endian format, the least significant digit comes first, so the same number would be stored as 54,321. That is 5 plus 40 plus 300 plus 2,000 plus 10,000. Due to the commutative property of addition, this yields the same final value. In contrast, a byte stream is analogous to a text string like Hi Phoenix. Since no numeric values are involved, there's no concept of most or least significant digits, and therefore no endianness to consider. The hashing process involves converting a transaction into a sequence of bytes, and using those bytes as the input to the hashing function. To produce repeatable transaction hashes, everyone must agree on the exact sequence of bytes that are input to the hash function. In order to achieve this, numeric values are converted to a sequence of bytes using little endian.